Hello all. So in today's class we are going to see about non-deterministic finite automaton. So this non-deterministic finite automaton can be in short called as NDFA or NFA also. Okay, so both are same. NDFA and NFA both are referring to the non-deterministic finite automaton. So what is this non-deterministic finite automaton? So here the finite automata which is not fixed or where we can't easily determine the next step, which we cannot determine the next step easily or we will get to the confusion. So because of that non-deterministic, because we cannot determine the next step from one state to another state. So why we will be struck in particular to this NFA or NDFA? Because the transitions from one state to another state will be more than one for same input symbol. So in my previous lectures we have said that so summation, which is nothing but the set of input alphabets. So say for example, we are having a state called as Q0, as we will make this as the final state. So I will take the transition from Q0 to this Q1 for this A input symbol. Also I will make or I will give the A transition for the self loop also for this Q0 state. So here the machine can't understand from the state Q0 if A comes as the input symbol, then whether to machine should take this loop path or whether the machine should move to this Q0 to Q1 state. So as it is, there are two transitions for this A input symbol. So the machine can't determine whether to take this loop or whether to take this particular transition. So because of that, the machine can't determine between these two paths. Hence, this is called as NFA. So in which the finite automata, it is having from individual state, it is having more than one transition for the same input symbol. So if the same finite automata is being written like this, that is from state Q0, the transition will move from Q0 to Q1 for A, and for B it will take self loop. Now this can be defined as deterministic. This is called as DFA, and wherein this is called as NFA or NDFA. Why? Because from the Q0 state, for this A input symbol, there is only one transition. From Q0 state, for A input symbol, there is only one transition. Wherein in this finite automata, from the Q0 state, for the A input symbol, there are two transitions. So because of this is called as non-deterministic finite automata, and this is called as deterministic finite automata. Also, in DFA, we used to say that for all the possible input symbols, we are supposed to show the transitions. So you can see here, I have shown the transition from this Q0 for A input symbol, right? From Q0 to Q1 it is moving. Also, I am showing for this B input symbol as a self loop. So from the state Q0, I have taken A, I have shown the transition for this A, and also have shown the single transition for this B. Also from this Q1, I have taken single loop transition for both A and B. Wherein here in the NFA, for both the input symbols A and B, from this Q0 state, for this A input symbol, there are two transitions. Also, we have not stated the transition for this B. So because of this, it is called as NFA or NDFA. NFA or NDFA. So here there are multiple transitions for this A. Also there is no transition for B. Okay. And also for this Q1 state, we have not shown any transitions for this A and B. So this is called as non-deterministic finite automata, and this is the difference between DFA and the NFA. Why we are supposed to study about this non-deterministic finite automata? Because it is very easy to construct when compared to the DFA. It is very easy to construct when compared to the DFA. Okay. Now, and also one more thing, that is practically NDFA will not exist. So we can't create a practical machine by using this NFA. Okay. But then what is the use of constructing this NFA? That is, further we can particularly solve particular condition given for this particular language. Then we can convert this NDFA to DFA. So NDFA can be converted to DFA. So wherein in real time machines, NDFA further can be implemented. So because of that, we are also interested in learning this NDFA. So now we'll see one example for obtaining a NFA. Okay. So the question given to us is, obtain an NFA to accept the following language, and the language is the language W, where W belongs to A, B, A and B raised to N, or A, B, A raised to N, where N is greater than or equal to 0. So this is the condition given to us. So initially, the W should have two particular conditions. Either it can start with A, B, A followed with any number of B's, because B raised to N where N is greater than or equal to 0. So here the possible strings I can get from this first set is A, B, A, then any number of B's means I can take 1B or 2B or 3B, anything. So here number of B's will be same with respect to this N value. Also A, B, A, I can have only 1B also. And also A, B, A only. Why? Because here B raised to N value is equal to 0. So B raised to 0 is 1, only A, B, A we got. So even this is also the possible string here for this first condition. We are given with OR. Also the machine can have, let us consider this as the second condition. So the machine can start with AB string followed with any number of A's. So here if N value takes 0, then it can have only AB. If it takes 1, then AB, A. If it takes 2, then AB, A. If it takes 3, then AB, A, and so on for N values. Okay. So now how to solve or how to obtain a NFA for this given condition. So initially, first we'll break up the given solution problem into two. That is, we'll solve or we'll obtain the NFA for this AB, B raised to N. Next, we'll solve this AB, A raised to N. So first we'll solve AB, B raised to N. Okay, well first initially we'll draw or we'll obtain a finite automata, that is NFA, for this particular condition. So let us take one state. We'll name the state later. Let us take one state, then another state. So initially the machine can take this A symbol. So I will take A. It is compulsory. It is compulsory for us that the machine should start with either with ABA or the machine can start with AB. So A then the machine can have B, then also the machine can have A. So this is a continuous string which is compulsory for us to have. So A, B, A we got. Now what is the condition? It can also followed with B raised to n, where n is greater than or equal to 0. So greater than or equal to 0 is nothing but we can represent this B raised to n as B star. So for star representation we are going to have the loop. So here I will take B because it is choice for us. If I want any number of B's, I can go with it. If I don't want, then for A, B, A only. For this particular string, I will wind up here only. So because of this, I will make this as the final state. I will make this last state as the final state. Okay. Now, one more condition which is given to us is A, B, A raised to n. So, A, B, A raised to n. So now in this particular second condition, AB is mandatory for us. So again I will take one state, then another state. I will take a transition for this A symbol A. Then again I will take one more state and I will show for this B transition. So AB is mandatory. I have shown this AB. Then A raised to n, where n is greater than or equal to 0. So when n is greater than or equal to 0, we can have the self loop there. So it can have any number of A's, and I will make this as the final state. I will make this as the final state. Now we are supposed to join this particular NFAs. We are about to join these two NFAs. So I will introduce a new state here. I will introduce a new state here. Rather than introducing a new state here, now we can clearly observe that both the conditions are starting with the A symbol only, isn't it? So what we will do, we'll merge these two states. We will make these two states as single state. Okay. So for that I will merge these two states as a single state here. Like this I will just merge these two states. So now we can see the machine can either start with, if it comes to this state, then it can go with this route or it can go with this particular route. If it goes to this route, then it can satisfy A, B raised to n, right? A, B raised to n, that is first condition can be achieved with this particular path. If the machine moves to this route, means it can satisfy this second condition, that is A, B, then A raised to n, where n is greater than or equal to 0. So if here n value takes 0, means the machine will only wind up with A, B, A, because for that it has reached the final state. Also, in this particular path, if machine enters to this, then A, B, the machine even can wind up here also for A raised to n. So now we have satisfied both the conditions, and I will name these states as Q0, Q1, then Q2, Q3, Q4 and Q5. So this is our ultimate NFA for the given condition.